let's see. Great. So let's get started. So we are happy to have Alex Belin from CERN. He's going to tell us about the gravitational path integral from the P2 deformation.
Great. Thanks a lot. Thanks for the invitation. It's great to be giving this talk. I should say that I feel a bit bad because it's, I guess most of you guys are either in a time zone where it's very early or in a time zone where it's pretty late, and it's sort of only comfortable for me. But such is the nature of
for us.
Yeah, I guess it depends on one's schedule. But in any case, it's really nice to be giving this talk today. So I'll be talking about a paper about I guess a few weeks ago with Aitor Lefkovich and Gabor Sorozi. Aitor, who is now at Google or at X, I guess, and Gabor that's with me at CERN. And before I get started, I guess I'll go a little bit against the instructions you just heard 2 minutes ago and say that really please do interrupt and ask questions. It's a bit tough to give these virtual talks because you feel like you're just talking to your screen. So it really also helps me if you just interrupt and ask questions if something's not clear or if you have more conceptual questions. So really, I would say don't hesitate. I've meant to give a pretty informal talk. So yeah, great. So let me get started. So, I think ADS-CFT has really been a super powerful tool to study quantum gravity. And one of the reasons for that is that, the natural observables that one computes in ADS-CFT are CFT correlation functions. Which are like elements of scattering processes in ADS. And one of the reasons that things have been so nice is that these operators here, sort of natural observables, are really local degrees of freedom of the CFT. Okay, and the operators, the CFT operators, are really meant to be asymptotic values of bulk fields. And they live in a place where gravity is switched off. So they're defined really as asymptotic values of bulk fields, and they live where gravity is switched off. Okay, so they sort of completely avoid the whole ordeal of trying to understand how to define local operators in a theory of quantum gravity, which is not a very diff-invariant object. So from that point of view, everything is really nice, and everything is quite convenient. Okay, and then this sort of at an abstract level is one of the reasons why ADS-CFT has been so useful to try to understand quantum gravity. But I'd say that at some times it's also a burden. Because sometimes the questions we actually want to ask are the ones that are maybe less well defined or more complicated. So you could ask what are local operators, or how close to a local operator can we define in quantum gravity? Or how do we define quantum gravity? So this is, ADS-CFT describes quantum gravity with sort of asymptotic boundary conditions. But you could ask, what is quantum gravity with Dirichlet boundary conditions? With Dirichlet boundary conditions at some finite distance. Or, maybe another way to ask this is, how do we move into the bulk? How do we move into the bulk? Now, these are all questions that are maybe a bit murkier, and it's not exactly clear that they're really well defined, but they're also sort of more interesting. Now, of course, a lot of work has gone into trying to understand these questions. For example, when we talk about local operators, well, at least semi-classically, there was the HKLL proposal, or maybe more recently, techniques like entanglement wedge reconstruction. And when we talk about, how do we move into the bulk? Well, it brings back early ideas like holographic RG. And the idea that, some maximal distance in the bulk is basically the CFT UV cutoff. Of course, we don't understand this very well, and part of what I'll talk about today is trying to understand this better. But these are sort of really the questions that we would be interested in, that are somewhat more complicated than what sort of vanilla ADS CFT gives you. Now, over the last few years, there's been really exciting developments. In particular, for ADS3 CFT2. And this really started, I'd say, with a paper by Magao, and I don't know if I'm pronouncing that correctly, Mazet and Verlinde, who made a connection with a particular type of irrelevant deformations of field theories and CFTs in particular, called the TT bar deformation. So the deformation is defined recursively, where if you take the derivative of the action at some value of the coupling lambda, this is given by forming the theory by a certain operator called TT bar. Okay, and this operator is really defined, it's made out of the stress tensor of the deformed theory lambda. And maybe just to be explicit, I'll write down what TT bar is. It's just particular contractions of the stress tensor. And this deformation is interesting in its own right, in particular in the context of integrability. So if you have an integrable field theory and you deform it in this way, then the resulting theory is still integrable. Another nice property of this theory is that if you place the theory on a circle and look at the spectrum of the theory, then the deformation is also, the deformation of the spectrum is known. So you just know the deformed energy eigenstates. And so there's some formulas you can write down for the energy spectrum, and what MMV realized is that, well, if you consider a black hole in ADS with some finite, with some R max.
Excuse me, just a
yes.
Yeah, a clarification of the name, because I'm not familiar with this.
Yeah.
So this is called TT bar only at 2 dimensions, right? Because it can be written as TT bar probably.
Yeah.
For CFT2. So for higher dimension, it has other name, or it's
yeah.
Also
I haven't said anything about higher dimensions yet. For now, we're solely in the realm of ADS, or let's say of CFT2. In higher dimensions, I'm going to call it T squared. There's no obvious TT bar in higher dimensions because things don't split naturally into left and right movers. But there's a sort of, we'll see that there's a sort of similar type of operator that you can define, at least in some cases.
I see.
And so I'll call it T squared. For now, I'm calling it TT bar, but it's quickly going to become T squared. Thanks. Good. So if you sort of compute the mass of the black holes at some, where you put the black holes in a finite box of size R max, then mass of the black hole, then you match this deformed energy spectrum. Okay, so they proposed that finite cutoff ADS is given by the TT bar or T squared deformation. So since we just talked about this was all a story in 2 dimensions, and it's very well founded. Even though the operator that we're turning on is irrelevant, the theory still has some very nice properties. You can track the trajectory up the RG flow, which is a bit unconventional. So this is all really nice in 2 dimensions. And so a very natural question, which was just asked, is what about dimensions greater than 2?
Alex, may I ask you something?
Yes.
You mentioned that calculating the mass of the black hole, you match it with the deformation of the spectrum.
That's right.
Yep.
That's right.
So how they calculate the mass of the black hole? They do some how they do it?
That's right. If you want, yeah, it's like an ADMS with a boundary.
And when they calculate this mass, they get one value. The spectrum, there are many states. With which one they match? How the matching goes there?
Right. So the idea is that there's some function of so the energies as a function of lambda equals to there's some function of the undeformed energies and the deformation parameter lambda. And on the gravitational side, there's the size of the black hole and the radial cutoff. So these get matched to these 2 parameters here. So you can consider black holes of various sizes or various, let's label them by the horizon radius, the size of the horizon radius, and then so there's let's say the 2 parameters would be the horizon radius and R max. And then these get matched, if you want, to the 2 parameters of the deformed energy spectrum, which is the deformation parameter and the bare energy.
Thanks very much.
Does that make sense? And of course, there's a very naive question that you can ask, is that, well, what happens when you try to make the horizon of the black hole bigger than R max?
Yeah.
And then it doesn't fit in the box anymore. And then at that level, the energy spectrum becomes complex. So that very nicely matches.
I see. Thank you very much.
Yes, thanks. This is great. Please continue. Yes.
One more question. Yeah. So if I compute TT bar's OPE with itself, do I get a closed system, or I start to generate more and more operators?
By the OPE, well,
yeah.
Yeah, go ahead.
So I mean, I was just trying to understand to what extent this is like a closed system that, I mean, if I do, say, conventional quantum field theory, I put in some irrelevant operators, and then I think then I do, say, for example, perturbation theory, I start to see the other operators being generated in the process. So I would just say I was wondering in what sense this is like, a closed system by itself.
Right. So I think things are a bit murky if you're at some finite distance away from the conformal point, because I don't know how to talk about the OPE directly. But if you're at the conformal point, then we already know that, the stress tensor doesn't take you outside. In some sense, the OPE between the stress tensor and, say, a Virasoro primary only ever includes that Virasoro primary family. So in some sense, it is closed. If you look at the OP between T and itself, you only get Virasoro descendants of the identity.
I see. Okay, thanks. Yeah, that answers.
Those are words that you can say at the conformal point. I don't really know what to say once you're at finite lambda, because the whole concept of an OP becomes murky, I think.
I see. And then since I came late, why does lambda appear as sort of like a lower index on your formula? I mean, so is lambda the coefficient?
No, this is just a label. This is just to say that these are the stress tensor. This is made out of the stress tensor of the theory at lambda. So it's really important that it's not just turning on an operator in the action. It's defined recursively. So you deform the theory by the T squared operator at that value of the lambda, at that value of lambda.
Thank you. And then the lambda, so for each value of lambda, you have a CFT? Or?
No, it's not a CFT. This is, oh, thanks. This is, maybe I should have said this. This is a dimensionful coupling. It's an irrelevant coupling, so when you turn it on, you no longer have conformal invariance.
I see, so only for lambda equal to 0, you're at the conformal fixed point, and then for
There's
lambda
a CFT,
non-zero, you're...
that's right.
Oh, okay, yeah, thanks.
Yeah. Great. Great. Please continue. This is great. Please ask questions.
Sorry, this is so rudimentary.
No, it's
sorry,
good.
sorry
This is these are the useful questions so that we make sure that we're all on the same page. So in higher dimensions, there's been a couple of different proposals, and the one that I'll be mostly following today is a proposal by Hartman, Kruithof, Chagoulian, like say 2 years ago. And they wrote down a deformation operator in higher dimensions. And so the formula looks very similar. So when you take the derivative with respect to this variation parameter, you get some operator that's turned on. Now this is in D dimension for some operator X. And I'll tell you exactly what X is in a little bit. But roughly speaking, X is like T squared. Okay, it's related to a quadratic operator in the stress tensor. Now, and again, they played similar type of games. They, computed the deformed energy spectrum, and they compared that to black holes in ADS and found a match. There is something that is important to emphasize is that in 2 dimensions, this operator is quite nice. It has some nice factorization properties. And you can really define it even away from the conformal fixed point. And so this operator we know sort of makes sense microscopically here. Maybe I'll write the word microscopically. In higher dimensions, the situation is more subtle. And it's not really clear that we know what this operator means. In general, there's not in higher dimensional CFTs an operator that looks anything like T squared. So this is where you need to start making assumptions, and this is where large N becomes crucial. Because in large N theories, there are quadratic operators. For if you have any operator, you can take its double trace. So there is an operator that looks like T mu nu, T rho sigma. It's a double trace made out of the stress tensor. And so this deformation that they wrote down, it makes sense at large N, or in the large N limit. It's not clear if it makes sense at finite N. So this is a very interesting question. And I will confess right away that I'll have nothing to say about this, unfortunately. So I'm just going to sort of work within the large N approximation. Okay, maybe at the very end we can discuss a little bit of what we've learned and whether it teaches us anything about whether this makes sense at finite N or not. But I'd rather be sort of upfront about this right away, and the question is still completely open, and I won't really address this issue too much. And what I'd like to do today is give a slightly new perspective on this deformation. Okay, and the new perspective will come by finding similarity between the flow equation of the partition function and the diffusion equation. And what I'll do today is solve this diffusion solve this diffusion equation by finding its diffusion kernel. Okay, and schematically, the answer will look like this. The deformed partition function as a function of lambda for the theory on some manifold with metric gamma is given by the integral transform with some kernel lambda of the partition function at a different value of lambda, lambda prime, which could be 0, for example, on some manifold with metric gamma prime. Okay, and so I'll show exactly what this diffusion kernel is, and in particular, what I'll show is that this diffusion kernel is given by the gravitational path integral with Dirichlet, between two Dirichlet boundary conditions. Okay, so that'll be sort of the main point that I'll discuss today. And before I really get started, I just want to say a few words about how we got into this in the first place. So the picture for the
excuse me, your
yes.
second lambda is lambda prime. So, but are you going to integrate lambda prime, or so how the lambda on the left hand side relates to lambda prime on the right hand side?
So you imagine going from so for example, lambda prime could be 0, right? So this is given a partition function at one value of lambda prime. This tells you how you sort of go from lambda prime to lambda. So if you want, there's sort of like initial and final boundary conditions.
So so this lambda prime sort of relates to gamma prime.
But yeah, I think formally I should put a lambda prime in here in the kernel as well. Yeah, sorry.
And are you going to? So you are not going to integrate over lambda prime.
Well, maybe this was meant to be a bit schematic for now. Maybe let me get to that exactly when we'll see that sort of only a ratio of gamma and lambda enters, and so I'll get to that. But I'd rather, this was meant to be schematic at this point. I'll of course explain all of this in glory details later.
Okay, thank you.
Yeah. Good. So the picture, if you know, if this is like Euclidean time, and this is the radial direction in ADS, the idea is that by doing this deformation, we're flowing into the bulk. And you know, we're considering the theory in these radial slices. Smaller and smaller radial slices, the more we flow. So this would be the standard TT bar or T squared deformation, what it does from the point of view of the bulk. Just flows into smaller and smaller radial slices. Now, the reason we got into this in the first place, the thing that we were looking for is we wanted to try to do something different. We were trying to, so we're considering overlaps of states prepared by the Euclidean path integral with some sources turned on. In this case, let's say the source is just a background metric. We were trying to look for a way to flow into the bulk that would look something like this. And in particular, we were very interested in this sort of special surface here, which sits at the middle. And the reason for this is that there's something that is now completely disconnected from all of the words that I've said so far, but there's a question of how to compute the extremal volume. So the volume of the extremal slice from the CFT. So Susskind has conjectured that this is dual to the complexity of a CFT state, but we were just asking, okay, how can we can we find a CFT prescription that would get for us the volume of this slice here? This is some Cauchy slice sigma, and you can ask, how do I extract the volume of this Cauchy slice? And so we're looking for something that flows into the bulk between the sort of piece of CFT data that we had, which is the background metric that you turn on, and we would flow inwards into the bulk in this direction here. And so this looks like it's a different kind of flow. In particular, it looks more like something that you would get if you could do a spatially varying t-squared deformation. Everything I've said so far was mostly about deformations where the deformation parameter lambda is a constant. So you do it equally at all positions of space-time in the CFT. And this would look something that is more like spatially varying. So can we define something like this? And we'll see in the talk today, I hope to get to that at the end, that this is something that can be achieved with our kernel. Okay, so this was sort of our motivation for getting into this, and then we got, well, a bit. So the talk will mostly not be about this. Will mostly be about deriving the kernel, but I'll say some words about an application of it for this context at the very end. Good.
Is
So
R the radial direction?
Yeah, R here is the radial direction.
So you somehow hide the another X direction?
Yes, sorry. Well, this would be a spatially, spatially, we're all in Euclidean, so really tau Euclidean is just a direction like the X directions, if you want. So when I mean spatially varying, I mean it would need to vary as a function of Euclidean time. Does that answer the question?
Thank you.
Can I try to understand the picture in the bottom? You're still taking like time slice of the bulk in the bottom.
The bottom here is one time slice of the bulk. That's right.
And V sigma is supposed to be the thing that measures complexity.
Well, V sigma is supposed to be the volume of that slice in the bulk.
Okay. Okay.
So so far there's nothing that relates it to complexity. Today I'll say nothing at all that relates it to complexity, but there's just a question of how would you capture that volume from the CFT degrees of freedom. And so this was just meant to be a motivation that it seems that you can flow, if you find a way to flow radially this way, the green way, then you flow from the background source gamma to the slice in the middle. And so then you can, once your theory is defined here, well, you can just sort of capture the volume. That was the rough idea, and I'll try to make that precise at the end of the talk.
I think I'm confused. Is that looks like a codimension 2 slice? The green line that goes through the diameter of the circle looks like a codimension 2 slice, right?
No, it's codimension 1, right? So in this case, the boundary is 0 plus 1 dimensional.
Oh.
The bulk is 2-dimensional, and this is a 1-dimensional slice.
Oh, okay, I see.
Space would come out of my iPad, I guess, out of the screen for you guys.
Okay, I see.
So this is a codimension 1 size. Yeah. Thanks. So what's the plan for today? Well, this was my introduction. I'll start by just reviewing the flow equation, showing a connection to the radial Wheeler-DeWitt equation, and give a slightly new perspective on this flow equation, like I said. Then I'll solve for the diffusion kernel and show that it relates to the gravitational path integral.
Excuse me, we don't see you writing, I think, something.
You don't see me writing. Oh yeah, it froze. Really? Thanks. Let me do it again. This has never happened to me before. Ha, does it work now? Do you guys see this?
Yeah, that works now. Thanks.
Thank you. Please, please tell me again if it freezes. Good. So what was I saying? Yeah. So I'll solve for the diffusion kernel and show that it's given by the gravitational path integral between the two slices. And finally, I'll talk about applications and how this connects to Hartle-Hawking states and ADS-CFT. And extremal volumes. Good, but let me just maybe stop here for now and ask if there are any other questions.
Alex, so everything you do today is a Euclidean signature, right? Is that right?
Up till the very, very end, well, I'll be explicit about it. Yes, everything I'm saying now is in Euclidean signature. That's right.
Okay, thanks.
Eventually, I want to talk about Hartle-Hawking wave functions, which is a more Lorentzian thing, but yeah, that'll be at the very, very end. So for now, everything is in Euclidean.
Okay.
Yeah, that's why when I meant spatially varying, I mean, you know, you need to turn on a t-squared deformation parameter, which is a function of the Euclidean, you know, space-time coordinates, and in particular Euclidean time. Good. Anything else? Great. So let me move on. So the flow equation. So let me just go back to what the deformation was. So the flow equation that Hartman and al. Wrote down was the following. And now let me be more explicit about what this operator X is. So this will be a bit complicated. So like I said, it's a composite operator, which is roughly the stress tensor, but it's a bit more complicated than that. TKL. Great, here we go. So this is the deformation operator. So let me just briefly say what the various objects that enter here are. This 4 index G is the supermetric, which has the following expression. Now, so it's just built from the metric gamma. Q is what will become later for us an induced metric, but for now it's just defined the following way. And AD is just some constant, which is just some constant that depends, say, on the number of dimensions. And this S counterterm here is the holographic counterterm action, but without including only terms that depend on derivatives of the metric. So this is the counterterm, but without, maybe I should put a twiddle, without the leading holographic counterterm, which is just the boundary cosmological constant. Good. And this is a bit complicated. So I'll consider a different partition function, a different flow equation instead. So I'll work with the bare partition function, which is really just multiplying the renormalized partition function by the holographic counterterm action. Again, without this leading counterterm. And so the renormalized partition function is nice because if you actually want to take things to the boundary, that's what's convergence, the renormalized partition function. But if you're working anyway at some finite cutoff, everything is finite to start with, so you don't really need the counterterm actions, the counterterms to the action. And so I'll work with this, if you want, bare partition function instead. And then the bare partition function is much nicer. It solves a simpler flow equation, which basically just removes all these counterterms all over the place. Okay, so the only things that are left are the terms that don't have these counterterms. And there's something else that's particularly nice about the second flow equation is that it has a scaling symmetry. So the solution to this flow equation is such that it has the following symmetry. If I rescale all the parameters in the following way, if I do a scale transformation, then this object is invariant. Okay, so this you can just check directly from the form of this flow equation down here. Now, because of the scaling symmetry, it's kind of natural to look for the following ansatz. That the solution to this should only depend on this ratio here, which doesn't get changed under scaling symmetries. Okay, so you can look for an ansatz of this type. And now you plug this into the flow equation. Before we had, so maybe I should say one thing. This is a bit like a diffusion equation, right? There's a simple derivative here with respect to lambda, but a double derivative with respect to the metric. When you plug in this ansatz for the solution, then you get rid of the lambda dependence, and you have an equation which only depends on derivatives with respect to the metric. And in fact, you can show that this function here basically solves the Wheeler-DeWitt, the radial Wheeler-DeWitt equation. And I'm not going to do this explicitly in the sense of time, but it's just taking this ansatz and plugging it in. Then you need to do just a small field redefinition, but otherwise this function solves the Wheeler-DeWitt equation. And again, this is not a surprise. This is the way that they derived this flow equation by using sort of the classical version of the Wheeler-DeWitt equation, which is the Hamilton constraint, and then using the scaling word identity. But the nice thing about this is that this is gauge invariant. And what I mean by that is I didn't need to use any specific coordinates. For example, there's no Pfefferman-Graham coordinates needed. And moreover, at this point, I can make lambda just any function of x. So if you want, this includes spatially varying lambda. Or perhaps said differently, considering a spatially varying deformation parameter is not more complicated than understanding the t-squared flow with a constant parameter, but on a curved background, because it's really only this dimensionless ratio that enters. Okay.
Just to make sure I understand correctly. So is this W equation is actually the same as this earlier holographic Wilsonian RG flow? If you write the Bach path integral, demanding is there's cutoff independence. You work out the flow equation in the Bach. Is that the same?
That's right. I mean, when I mean the Wheeler-DeWitt equation, it's literally the radial Wheeler-DeWitt equation solved by the solved by the partition function, as you would see in holographic RG. Again, modulo some minor field redefinition that you need to do, but that's right.
Okay, thank you.
That's right. Yeah. And again, this is what I really did. I didn't really do anything here. I sort of reversed engineer the way that they derived this flow equation in the first place. You guys are again not seeing when I change slides. Not seeing it move, right? Sorry, I have to. I don't. This is the first time that it's done this to me. I don't know why. Good. Now I see. Good. So again, this is really just reverse engineering the way that they solved for this equation originally, but it makes it more it makes it more gauge invariant and manifestly gauge invariant, because really what you have is just a function of this ratio here. So maybe I should be explicit that these things are allowed to depend spatially on the Euclidean coordinates x.
Sorry, does x include time?
Yes,
or
yes.
Is it just
is tau Euclidean plus x spatial. Yeah.
Oh, okay. There's a question in the chat box I saw. It says, do you require lambda x to be greater than 0?
Yes. Let's do that. Yeah. Yeah. Maybe I'll say something at the very end about flipping signs of stuff. But yes, for now, let's consider lambda to be greater than 0. Good. Okay. So like I said, again, there's nothing really new here. It's just sort of a rephrasing of what Hartman et al. Already did, but it sort of makes the nature of the gauge invariance more manifest and doesn't require Pfefferman Graham coordinates or anything like that. And in particular, it suggests a way of how to deal with spatially varying deformation parameters. So now let me move on to the second part, which is solving for the diffusion kernel. Okay, so I'm rewriting this many times, but the flow equation of this bare partition function is simpler. And now what I'm going to do is do a trick, which is do a Hubbard-Sratanovich representation of this flow equation. Square root of q r cubed z. And so this flow equation is really equivalent to doing the following, saying that z of lambda plus delta lambda so now d over lambda divided by some normalization. So what you do is you introduce some fiducial, some Hubbard-Sratanovich field H, which we integrate over. H squared minus Hij z. So this is times z of gamma plus H. Okay, so now we're just introducing some fiducial field H that we're going to integrate over with this Gaussian weight up here. And you can just easily check that doing this just produces for you exactly the flow equation, right? Because basically you have a Gaussian integral here, h squared, so you're going to take sort of double derivatives of z with respect to the metric, and that is what generates the stress tensor. So you can just work this out, that this is completely equivalent to describing the t-squared flow. Oh, and I didn't tell you what the normalization is. Normalization is just basically the Gaussian integral itself. Good. And now to sort of solve the diffusion kernel, well, we'll just iterate this. Okay, so we're going to define delta lambdas, which are lambda over n. So little steps. We imagine going from let's say lambda equals 0 to some finite lambda, and we split it up in n steps. And then, so what happens to the partition function? Well, we just sort of iterate this process n times. So let me just write it here. You just get the product of these integrals over these fiducial variables hk. You get this product over the normalizations. Okay, then you get hk squared minus, sorry if this is a bit hard to read. Okay, you get the product of all these things times the partition function with 0 coupling, but with increasing change in the metric. So basically, this is just iterating step by step this Hubbard-Stratanovich trick to generate the flow equation. And you can do this, so we split the path from 0 to lambda in n steps. And then we'll want to go to the continuum. So the next step is to go to the continuum. And for that, we make the following identifications. Well, we define now a continuous variable eta, which will be, eventually it'll become the radial direction in the bulk. So the little steps are still labeled by 1 over n, and eta will go between 0 and 1. Now the little steps in coupling space, again, they can depend on the Euclidean directions. They're given by some function that I'm choosing, that I'm calling mu, which again is just mu of eta and x. And mu is really the path that we're taking in deformation space. So, you know, lambda of x you get by integrating this mu of eta from 0 to 1. Of course, if you wanted, you could also stop at some intermediate values. So maybe I should define this deformation parameter that stops at some value eta. Okay, and then you need to do some small field redefinitions. So I'm sorry if this is slightly technical, but these are the steps that need to be done. You redefine these HS fields in the following way. And then now we can define now a metric, which now basically becomes a d+1 dimensional metric by integrating this big H field. Okay, so maybe this sounds a bit out of the blue for now, why you would want to do these field redefinitions, but just bear with me for 1 second, and we'll see what happens. So after you do all of this and the dust settles, what does the partition function look like? And maybe let me maybe be really explicit about the fact that it's lambda of x here. So we did a field redefinition. So now the things that we integrate over are these d+1 dimensional metrics gamma. Eta goes from 0 to 1, and we integrate over these metrics. There's the normalization factor that I won't say too much about now. And then there's 2 terms. The first came from this Ricci scalar that we had. So if you just look what happens, it looks like this. Square root of q RQ. And then there's another exponential. which came from these terms that went like h squared. I'm almost done. Okay, and then times z at gamma of 1. Okay, so this is just a rewriting. I took this Hubbard-Stratanovich trick to write the flow equation, then I iterated it a number of times. I took a continuum limit, and then I arrive at the following expression. And this is really some kernel that tells me how the deformed partition function behaves as a function of gamma 0. Okay, and in just 1 second, I'll rewrite this as the gravitational path integral. But before that, I just want to make a comment, is that there's always been the question in holographic RG of, if you go to some finite radial distance in the bulk, how does this relate to something like Wilsonian RG, which would be integrating out the high momentum modes in the CFT. And here we see that what you do is in fact a little bit different. What you do is, instead of integrating out the high energy modes, really you're smearing the boundary metric over some distance, which is labeled by this lambda. So in some sense, you can't, the theory is becoming non-local. You've smeared it over some region of size lambda. And this is exactly what this kernel is implementing. And so, it's not really that you've integrated out high energy degrees of freedom. It's rather that you can't resolve locality below this scale lambda. So this is really one way that you should think about what this kernel is doing. And now this kernel might not look to you exactly like the gravitational path integral yet, but it's starting to be very close to it. And to make it maybe more manifest, what you can do is the following. You can now pick a gauge for the metric.
Sorry, are you claiming this kernel can be viewed as some certain region of bulk path integral during 2 slides?
Yes. I'll show that now. It's not quite manifest yet. You have to, depends how much you love the Gauss-Codazzi equation, but it's not quite manifest yet. But it will be in 1 second.
Alex, I think your slides are stuck again.
They're frozen again? No. What is going on? Okay. This has never happened to me. Okay. Give me 1 second. Is it not working now? Can you still hear me? Hello?
Yes.
You hear me, but you can't see the...
It just says you have started screen sharing.
I have no idea what's going on. So let me stop. Oh, Zoom was bound to break down on me one day. I'm really sorry about this. I don't really know what to do because I don't have slides either.
Do you think restarting the meeting?
Hold on,
like,
hold on.
Oh,
it
okay.
works now. Sorry. Okay. Well, yeah, I'm sorry about that. I really don't know what's going on. It's just seems to be something wrong with the iPad. Okay, so what I was saying, and I'll try to be quick now because I've lost some time. So this doesn't quite look like the gravitational path integral yet. But you can turn it directly into the gravitational path integral by, for example, picking a gauge like this. And then you just pick these functions in the right way. So you just make the following identifications. And then when you do that, what happens is that basically this becomes the trace of the extrinsic curvature squared. This becomes Kij, Kij, plus some other terms. And this here is just, again, so these things sort of go away. And this is just R of the induced metric Q. And then you can use the Gauss-Codazzi equation. So let me just write it down. So what you get is something like this. Plus some S rest. Okay, now you can just use the Gauss-Codazzi equation. And this thing is nothing else than the d+1 dimensional Ricci scalar plus 2 times the trace of the extrinsic curvature evaluated at the endpoints. In other words, this is the Gibbons-Hawking term. And from S rest, there's some pieces that are left over because of the way we've identified the variables here. And there's some pieces that are left over. And what you get from here is the cosmological constant. And you even get the leading holographic counter term, which, as I said from the beginning, is treated a bit differently from this S rest. Okay, so in other words, this kernel that we had, the exponential here, what it becomes is simply the Euclidean path integral between two surfaces, and you have these boundary terms, of course, here, the counter terms and the Gibbons-Hawking term. So the kernel becomes the Euclidean path integral between two slices with Dirichlet boundary conditions. So to be maybe more explicit.
So is this result, is the your solution of the your solution of the flow equation diffeomorphism invariant in the bulk, or is this result rather depend on your gauge choice?
Yeah, so it almost is. I want to get back to. I'll comment on that in 2 minutes, and I won't have much more time, I guess, because I'm slowly running out of time here, but or rather quickly running out of time. It's almost gauge invariant, and I'll say. So let me maybe just say something quickly about that now. So again, the thing looks something like this, where the kernel has now become this Euclidean path integral over the metric. And now here I can just rewrite this as a function of the induced metric instead. Q of 0 is this, which is like an initial condition. And so it is diffeomorphism invariant. So you can see, so if you want, we picked a gauge, right? I wrote down some metric here where we picked a gauge. But you see that you get the Euclidean path integral, which is manifestly diff invariant. So yes, this is d+1. So everything was manifestly d-dimensional diff invariant, but you get something that's now d+1 dimensional diff invariant. There is, however, a question about this term here, and there's a question about the measure. And I'll comment on that just on the next slide, but I just wanted to say that this is sort of, if you want, the main result in our paper is that by iterating this Hubbard-Srutanovich trick and making the right field redefinitions, you can obtain this is the diffusion kernel. And what the kernel is the gravitational path integral with Dirichlet boundary conditions on both sides. Okay, so let me just make some comments. So there was this question of whether it is diffeomorphism invariant or not. And the exponential part is, the action part is diff invariant, but the measure is not quite D+1 dimensional invariant. So the measure, what you get is not something, it's not the gauged fixed D+1 dimensional diff invariant measure. What you get instead is something a bit peculiar that I was not familiar before this. You get a measure that is apparently quite known to people that study the Hamiltonian path integral. And it's in the context of the Hamiltonian path integral, it's more like the flat measure that would look something like this, where n, I, and n are the shift and the lapse. So you get basically you get a gauged fixed version of the flat measure like this, provided that there's actually a condition on the paths that you take in lambda space, provided that this splits into a function of lambda and a function of x. Okay, so what we seem to get out of this is that by carefully looking at the measure, the only way that the whole object you get is really D+1 dimensional diff invariant is if the path that you take in lambda space has this form. But note that you can still take, so what this is saying is that, you know, you should sort of originally fix some profile as a function of x, of the Euclidean coordinates, and then you flow into the bulk with some function f of lambda. But you can't do it sort of at arbitrary stages any way you want as a function of x. But that's okay, because again, remember that at the end of the day, everything was just a function, you know, the Wheeler-DeWitt equation was just a function of the induced metric divided by this lambda. So you can still obtain any deformation parameter you want, just you have to do it in a particular way. Okay? But provided that you satisfy this condition, yes, you have D+1 dimensional diff invariance. The second condition, the second comment I wanted to make is what is really the nature of this bulk that we've found? So what I showed is that there's this t-squared deformation that makes sense at large n, and by, you know, iterating it, you can obtain the gravitational path integral. But is this gravitational path integral that we're finding really the bulk dual, or is it like a sort of fake bulk? And in fact, I think except under special circumstances, it's more like a fake bulk, because one way to see this is that I've used the large n assumption such that the operator t squared exists, but nowhere did I use, for example, strong coupling. So, you know, one thing that I could do is I could take n equals 4 super Yang-Mills at weak coupling and deform by this operator and still get the gravitational path integral. And we know that, of course, weakly coupled n equals 4 super Yang-Mills is not well described by the Einstein-Hilbert action. So in some sense, so what I would say is that the bulk that we find is in general fake. This is a deformation that you can do to any large n CFT, but it only becomes the true bulk, the true ADS bulk, provided that some other conditions are satisfied. For example, strong coupling, etc. So those were the two comments that I wanted to make, and I see that I'm basically out of time. So can I have two more minutes?
Yes, please. Yes, please.
Okay, sorry. I just wanted to say 2 words about obtaining the volume and Hartle-Hawking states. Great. So something that I said at the very beginning about my motivation is that, you know, you can consider turning on a background metric, which produces an excited state in the CFT, and the gravitational path integral with these boundary conditions would compute for you the unnormalized overlap of 2 states. And the type of flow that I talked about, where you can make things vary over the Euclidean directions, you can sort of consider overlaps now of the following type. And in particular, you can consider the following overlap. And this object here, this is very natural in ADS-CFT. This is nothing else than the Hartle-Hawking wave function of a state that we call gamma, prepared by the Euclidean path integral, as a function. So this is the Hartle-Hawking wave function of the state gamma for field configuration Qij. Okay, and this is something that we can write very naturally now thanks to our diffusion kernel. So you can write it the following way. The idea is that you multiply by the counter terms, but only on the south pole, meaning you only multiply by the counter term action down here. And now you put the radial Wheeler-DeWitt wave function for the following values of the metric. Okay, so this gives you a relation between Hartle-Hawking wave functions and these radial Wheeler-DeWitt wave functions flowed in the appropriate way. And in particular, you sort of flow only with respect to the northern hemisphere. And so what you can do with this is you can then find a prescription to compute extremal volumes, and I'll be very schematic because I'm really out of time and I don't want to go over time. But the way to do this is that instead of keeping track of the scale of the metric, what you want to do is keep track of the trace of the extrinsic curvature. And so you can define a different type of Hartle-Hawking wave function with different boundary conditions, if you want, where you fix instead the trace of the extrinsic curvature. And this is done by doing the Laplace transform with respect to okay, and theta is basically the trace of the extrinsic curvature. So you do this Laplace transform, and now this is a Hartle-Hawking wave function, but with different boundary conditions, where you fix the trace of the extrinsic curvature instead of fixing, it's a Dirichlet condition for the extrinsic curvature instead of a Dirichlet condition for the metric. And semi-classically, this object evaluates, if you just look at the semi-classical limit, this action is a boundary term, and it's just given by the following. It's just given by the trace of the extrinsic curvature times square root of the induced metric. So then you can write down the following expression. If we take the k derivative of this expression, and evaluate it at k equals to 0, which is the extremal slice. That's the definition of the extremal slice. then you obtain the extremal volume. Okay, and all of these objects in principle have a CFT writing that you can write down in terms of, you know, this t-squared deformation. So if you wanted to take this extremely seriously, one could say that this gives a CFT way to compute extremal volumes in ADS CFT. The problem is that to solve this flow equation, the best way we know of how to solve the flow equation is to solving Einstein's equation. And once you solve Einstein's equation, well, you can just go and compute the extremal volume yourself. So this is a little bit formal. Formally, it is what it is. It's a way to rewrite the extremal volume in terms of CFT quantities using this t-squared deformation and diffusion kernel. But it's not clear that it's very practical because it requires really, in fact, solving Einstein's equation, which is what the bulk would do, which is how you would do the bulk computation anyway. So I'm really over time. I'm sorry again about the technical difficulties. I don't know what happened with my iPad and Zoom, but I'll stop here and I'll thank you for your attention.
Thank you very much.
Could I ask a question or a couple of questions?
Sure.
Yeah. So Alex, thanks very much. I have two questions. Let me ask the first, and this maybe motivates another one. So you mentioned at some point towards the end of your derivation that you have, under some conditions, this is a couple of transparencies back, a non-invariant measure, right? So you wrote your thing and you had it. So this non-invariant measure usually suggests anomalies, right? So having an action that is invariant and a measure that is not is one way in which anomalies manifest. Do you see this thing you have there in the green box as a way of avoiding an anomaly? And in this case, maybe it's diffeomorphism invariance anomaly, right?
Yeah, that's a great question. I don't think I have anything smart to say about it. Yeah, maybe it's what you're saying. It's related to trying to cure some anomaly that you would get from diff invariance.
Good.
But I don't know why one would have expected such an anomaly in the first place. So
yeah.
So yeah, I mean, yeah. All I can say is this is what it is. It suggests what you're saying, but I don't know how to say anything sharp.
Let me ask you another one. Suppose that, as you said, you go to the correct regime, right? So you take large N, you take strong coupling, and you take N equals 4 super Young MIPS, right? With this, you will generate a bulk, right? That will be ADS5, right? But let me ask you this. You are deforming the theory by an irrelevant, right? The t-squared. So why would you get ADS5? Shouldn't you get something where the ADS5 is actually broken somewhat? But by which I mean, let me tell you the example I'm thinking. Keep the 1 in the work factor of the D3 branes, right? That keeping the 1, it's an irrelevant operator, it's a dimension 8 operator, right? And what it does is undo the ADS5 into flat space, right? So why here you are getting ADS5 even if you are deforming your theory with an irrelevant?
Yeah, that's a good question. So this is a bit different than trying to recover the flat space supergravity far away, which is something that you'd like to do with irrelevant operators. In this case, what you're really doing you are in some sense destroying the ADS, right? Because you're really, I mean, you had some sort of asymptotic ADS boundary conditions, and by flowing into the bulk, you sort of destroyed that.
Okay.
Right. So you've changed the rules of the game for the boundary conditions. I agree that it looks very different than I agree that it looks very different from the type of things that you'd like to do with recovering the flat space limit, but I don't know exactly what else to say.
Yeah. Okay.
That's an interesting question. They seem that they're of different nature.
Maybe related to this, suppose that you take n equals 4 supergames. Do you see the S5 somewhat?
Yeah, so sorry, that's the other thing that I wanted to say, which is a great part of the question. So in fact, even if you take n equals 4 at strong coupling and you do this deformation, you don't really flow into the bulk. Why? It's because n equals 4 doesn't just have gravity. It has a bunch of scalar field, and in particular, it's what you're saying. It has an S5, right, which generates an infinite tower of KK modes. So really, if you wanted to flow into the bulk, you would also need to produce the path integral for all these other fields.
Okay. Okay.
So you would look
clearly in the scalars will be this 5 encoded and etc. Right?
Exactly. So what you would need to do is, you would need to do a t-squared deformation and add to it probably a bunch of O squared deformation, all for the fields. And I presume this can be done. I mean, certainly in the paper by Hartman and friends, they looked at they looked at scalar fields as well. And I presume one could do this diffusion kernel trick for them as well, but we haven't done that.
This t-square you wrote is made out of what?
This is just the stress tensor in the CFT.
Okay, but in n equals 4, the stress tensor, if I were to write it, it would include the contribution from the scalars and the fermions, right?
Oh, sorry. But by scalars here, I don't mean the 6 scalars of n equals 4. I mean really all the single trace operators.
Okay.
These are
very
like
good. Very good.
You know what I mean?
Okay. Yeah. Very good.
So you would need to add all of those.
Good. Very good. Thanks very much. Thanks very much.
So can you say something about how to relate the Hamiltonian measure with your measure from the flow equation?
Yeah, I mean, basically, so this is, this would be a bit long and technical, but basically you take the measure that we have, and you can interpret it. So remember, we picked a metric, right? Let's see, I have that somewhere. We picked a metric here, right? So there's some gauge fixing. So what you can do is you can take this measure that we obtain, which is up here. You take this measure that we obtain, you write it down, there's an explicit expression for it. And then you can show that it boils down to the flat measure of this type here, with a gauge fixed version, so like with a Fadeev-Popov determinant, provided that you satisfy this condition. That's sort of how the story goes.
And I guess it is a Hamiltonian measure if you do the foliation. I mean, in the radial direction, right? I assume.
Yeah, that's right. That's right. Absolutely. Yeah. It's Hamiltonian in the radial sense, right? Just like the Wheeler-DeWitt equation is a radial Wheeler-DeWitt equation.
Thank you.
Yeah. So time here is basically the bulk radial coordinate. Yeah.
One more. You made a comment about some loss of locality given by the scale that this parameter lambda introduces, right? Can you repeat it? So it was something along the lines of losing the Wilsonian version of things.
Yeah, so I was saying that, there's been a question in holographic art. So what people typically say is that, R max is the UV cutoff in the CFT. And by UV cutoff in the CFT, you might mean something like, well, you integrate out high momentum shells all the way down to 1 over epsilon CFT. That was sort of the old picture of what holographic RG is doing. And I think this t-squared deformation gives us a slightly different picture. It's saying, well, what the bulk is at finite cutoff is not, is not just Wilsonian RG in the CFT, it's rather taking the CFT partition function here, which is a function of, you know, the metric, and then you smear over the metric. And in some sense, you do lose high energy modes because you can't resolve locality arbitrarily well anymore, because you've smeared the metric. So, you know, very high energy degrees of freedom, you'll have a hard time localizing them, but it's a slightly different picture than momentum shells. It's more like a smearing of the metric. So I think what this T-squared operator suggests is that that's more what's happening in holographic RG. It's more like a smearing of the metric.
Thank you.
Oh, sorry. Can I just clarify? When you do the in the last part of the talk where you were talking about the extremal volumes, I'm confused whether that is volumes in the real ADS space or the fake space.
Right. So yeah, thanks. That's a great question. So I think it depends, you know. So it goes back to this question of whether it's a fake bulk or not. So, you know, I think if you take n equals 4 at weak coupling, you do this T-squared flow, and then you write down this formula here. You write down this formula here. Well, that will have nothing to do with the volume of the Cauchy slice in the gravity dual. So in some sense, what this captures is the volume of the fake bulk. But if you're in a circumstance where the fake bulk turns out to be the real bulk, you know, because you're at large N and you're at strong coupling, and say because you didn't turn on any matter fields, so you don't need them to do this flow, then it captures also the volume of the real bulk. Does that make sense?
Yes, but doesn't that suggest that there is some kind of Einstein dual, even if it has it is at weak coupling?
Yeah, I think, well, it means you can do something to your CFT that looks like it's transforming it thanks to the Einstein gravity dynamics, but it's not really clear to me what that means. This is something that we explored a little bit, and we don't know what that means. What if you take n equals 4 at weak coupling and you do this flow? What are you doing to the theory? Are you doing something nasty? You know, if you have nice semi-classical states, are you making them very not semi-classical anymore? What exactly are you doing wrong? We don't quite know. So I think that relates to your question. Yes, in some sense, there is an Einstein gravity. There's like an auxiliary Einstein gravity ADS space for all large N CFTs, but we don't really know what to make of it, I'd say.
I see. Thank you.
So is the large N parameter entering the path integral? For example, something in front of the action.
Yeah, so that's also a good question. So the gravitational path integral has a G Newton and an L ADS, right? Which in the dual CFT is labeled by N, and so it's really a question of it's really a question about how you're mapping to these parameters here. So there were some squiggly lines here. There's coefficients out front, and that's where really the G Newton goes, which is basically the n squared of n equals to 4. So you also engineer, I mean, you make that choice once, but you also engineer that in order to get it the right way. Yeah, I don't know if I answered your question.
But I just didn't see it very explicit that this parameter n appears in the kernel.
Yeah, so you didn't see it explicitly. So basically, what happens is the following. So so you can put sort of a xi out front here, which is just an overall constant out front of these. So this is the functional dependence. It tells you how omega depends on lambda, but let me put some constant out front that I'm going to call xi, okay? And the way xi appears is that xi appears out front here. It appears all the way out front of the integral. in the
So
action.
it's like rescaling of the metric gamma.
Yeah, it's like an overall rescaling of the induced metric. The thing is that you go from the CFT metric gamma to some induced metric that I've called Q, and when you do that, that's where you sort of put in the factors of G.
Okay.
I think the way people have sort of said it previously in these previous TT bar T squared papers is that you just put it in the deformation parameter lambda. But I like to think about it this way: is that you don't need to do that. It's just in the final step when you go from when you actually sort of want to write down an explicit metric. That's where you put the factors of G.
Okay, I see.
But it's a question of convention, I think, for the most part. Yeah.
Okay. Thank you.
Yeah.
Do you think that under this deformation, say n equals 4 superior mills will still be integrable? You mentioned the analogy with the TT bar in 2 dimensions, and is there any feeling about the fate of integrability under this deformation?
Yeah, that's another great question. The reason I'm a little bit hesitant is because that in higher dimensions, we don't really know if this T-squared operator makes sense. I mean, it makes sense at large n, and you might say, well, integrability anyway probably is just also there at large n. So maybe there's some hope. Yeah, I haven't really thought about it. It's a good question. I don't think I have anything smart to say. I haven't thought about it. I'd say I would want to say, provided that the deformation makes sense, I would expect it to preserve integrability. But yeah, since it's not clear that it makes sense, that's why I'm a little bit hesitant.
In 2D, the integrability is preserved because of the factorization properties of the operator, right?
Yes.
Yeah, so in higher dimensions, unless we study the factorization properties of this operator, only then we can say something about integrability. Maybe.
Yeah, that's why I'm a bit hesitant. I mean, the way it worked in these the way it worked in these papers. Sorry, my tablet. Can you guys still see? No, now it froze again. But maybe I don't need it anymore. So the way that it worked in this paper when they matched the black hole spectrum in higher dimensions is that they said, well, we need to evaluate the 1-point function of the operator T squared. And then what they use is that in a large N theory, in a heavy state, the expectation value of T squared is equal to the square of the expectation value of T, which is like the factorization property you're talking about. But that's very much a statement about heavy states. If you're in a light state in the theory, then there's a bunch of corrections that could be important potentially. So that's why I'm a little bit hesitant. Whereas in 2D, it's based the factorization is based on something else, which is much more powerful and much more robust.
Yeah. Thank you.
Other questions? If not, let's thank Alex again. Thank you very much for telling us about this very interesting story. It's very beautiful.